So in this section, we're going to take a look at the same thing we did yesterday, limits, but from an algebraic viewpoint instead of a graphical or numerical viewpoint. So I just want to emphasize that what we established yesterday is true for every single function. If you want to find the limit of a function, you could graph it and just read it, or you can make a table of values. But, you know, in the field, in the real world, that can be tedious sometimes. Who wants to make a giant table for every single limit? Who wants to graph every single function just to find the limit? So there has to be an algebraic way of doing it, and there is. As we sort of did yesterday, we saw that the limit, even though the idea is that we don't look exactly at the function output at the x value in question, if it's a quote nice simple function, 99.999% of the time the limit will equal the function output. So that's one way of at least attempting to find limits. If the function is quote nice enough, the function output is usually equal to the function limit at that x value. Now this is very ambiguous, this is very vague. What does quote nice mean? Again, that's why I said this is sort of like an informal idea. You will formalize things next year when you take calculus. So if I had something like this, you know, find the limit as x approaches 3 of, I don't know, 2x cubed minus 10x minus 8. Well, that should be easy, right? The limit as x approaches 3 of 2x cubed minus 10x minus 8, the first thing I would do is straight up substitution. Now, this is my little forewarning to you. If you do any algebraic manipulations, you have to constantly write the limit down. You always have to write LIM, LIM, LIM. The only time that you can stop writing it is if you apply the limit, that is to say, if you substitute. So in this particular instance, my very next step is substitution, so I'm going to stop writing LIM. So I'm going to substitute the 3 in, and then just do math, right? So what's that? That's 27 times 2 is 54 minus 30 minus 8. So that's 24. So that is 16, right? Easy peasy. You know, the limit as x approaches, say, 1 of x squared plus 5x over x to the 4th plus 2. It can look like a crazy complicated rational function, but notice x is approaching 1. It does not make the denominator equal to 0, so that we know that 1 is a perfectly fine number to plug in. So you can go ahead and plug that guy in. You get 1 squared plus 5 times 1 over 1 to the 4th plus 2. And you get, what's that, 6 over 5. So that is sort of like, I know it's sort of a big pain. I made you guys do all those tables yesterday, and then today's lesson is, hey guys, if the function is nice enough, you can just go ahead and just plug it in. But remember, it only works out when it's nice enough. What if it isn't nice? You know, let's do one. Let's do a throwback to yesterday's lesson. This lesson that we did yesterday with a table. All right. Find the limit as x approaches 1 of x minus 1 over x squared minus 1. And we had to do with the table because when you plug in a 0, plug in a 1 in for x, you get a 0 in the bottom. But we also get something else here. This is sort of special. If you just plug in a 1, not only do we get a 0 in the bottom, but we get a 0 in the numerator as well. We get 0 divided by 0, and this is sort of special. If you got like 2 divided by 0 or 5 divided by 0, then yeah, you can't do that. But when you get 0 divided by 0, this is, Let me go ahead and do this here. 0 divided by 0 is called indeterminate form. Literally, we cannot determine that value. It could exist, it could not exist. We don't know. Now, this is not the only way indeterminate forms come about. So there are a handful of ways where indeterminate form can exist. You'll learn about them next year in calculus, but one of the common indeterminate forms is 0 divided by 0. So what? What does that mean? That means anytime you're evaluating a limit, if you get indeterminate form, this usually means you can simplify slash cancel slash rewrite something before finding the limit. So when you're doing limit problems, and you get 0 over 0, that doesn't mean give up. That doesn't mean graph it or go to the table, although you could. I personally don't want to do that because that's a lot of work. But 0 over 0 means, hey, you got to go back to the original problem, do something algebraically, an algebra trick, a numerical trick, something, so you can rewrite the problem so you can then evaluate further. So let's go back to the problem. It said find the limit as x approaches 1 of this function. I do all my work here, and I get 0 over 0. So that means I have to stop scratch work on a side. So I am done with this work here. So this work was a dead end. So my scratch work, I'm going to go, okay, let's take a look at this function here. So what can I do to it? What can I simplify? What algebraic thing can I do? Well, one thing you can always do, especially if you have a rational function, is to factor. Because when you have a rational function and you hear or your idea is to simplify, 9 out of 10 times it's factoring. Well, fortunately, the denominator is factorable, right? This factorizes into x minus 1 and x plus 1. And then you can go ahead and see that you get 1 over x plus 1. So this is scratch work here. So we got to sort of write out our formal work. So these limit problems are sort of like proofs. Don't just plop down the final answer. Go from start, middle, and end. So we have the limit as x approaches 1 of x minus 1 over x squared minus 1. The thing we say we're going to do is we're going to factor the denominator. Because I didn't apply the limit yet, because we're not doing the limit step, I still have to write LIM. Then we cancel. Because I'm not evaluating yet, I still have to write LIM. And now I'll go ahead and plug it in. And because I'm doing the substitution step, I can drop the LIM and then just go straight to 1/2 as we expected from yesterday. Right? So that's just a little nitpicky thing, but I promise you every single calc teacher will look for that. If you do not write these limits here, it tells the reader you've applied the limit when you really haven't, so they will deduct points. They will mark it off as wrong. So you have to constantly write LIM every single time until you actually evaluate it. Let's do another example here. Suppose I ask you to find, the limit as h approaches 0 of 3 plus h squared minus 9 all over h. So I'm not going to write it, but hopefully we can do it mentally. That in this particular problem, we can't do direct substitution. We're going to indeterminate form. Because if you make the h a 0, 3 plus 0 squared is 9. 9 minus 9 is 0. And then, of course, h is 0. So we get 0 over 0. So that usually means before we apply the limit, we have to do some mathy stuff. Now, there's nothing to factorize. It's rational functions. So the only thing that we can do is just do algebra. Let's go ahead and expand the numerator. So I'm going to go ahead and expand 3 plus h quantity squared. Hopefully after doing binomial expansion, we're a bit faster at this. It's the first guy squared plus twice the product plus the last guy squared. So if you were to expand this guy out correctly, you're going to get 9 plus 6h squared plus h squared minus 9 all over h. Hopefully you can see that the 9's cancel out. And then hopefully you can see that we can factor out an h from the top and cancel out with the bottom. Right, so we're going to reduce or cancel out one h, so we're left with 6 plus h. Notice I kept writing limit because every single one of these steps is doing an algebra step. Now I can go ahead and apply the limit. Now I can go ahead and substitute h equals 0 to give me a limit of 6. Let's do one last example. This is just another thing that you might, another trick that you might need. Suppose I ask you to find the limits as, I don't know, x approaches 0 again, of the square root of x squared plus 9 minus 3 all over x. So let's start our work here. It's sort of like a proof. Plus 9 minus 3 all over x. Again, I'm not going to write it down, but mentally we should know that we can't do direct substitution because you get a 0 on the bottom. And then if x is 0, this whole guy is 9. When you take the square root, it's going to be a 3. 3 minus 3 is 0. So we end up with indeterminate form, 0 over 0. Now, this is just a common trick that, or a common technique that you just simply need to know. If you have indeterminate form and there's a radical piece, it's just like one of those automatic instant thing. You know, if you see a quadratic, you automatically go to factoring. Well, when you see a binomial with a radical in its indeterminate form, 9 out of 10 times it's going to be conjugates. You know, conjugates, that's one of the, solutions to life. When in doubt, if you're stuck, do conjugates. So we'll do limits as x approaches 0 of x squared plus 9 minus 3 over x. And you always do the conjugate of the thing that has the radical binomial. So which in this case is the numerator. So we'll go ahead and do radical x squared plus 9 plus 3, radical x squared plus 9 plus 3. When I do this, I typically do not multiply out the non-conjugate. So I'm only doing algebra here, so I have to rewrite the limit. We should know the product of two conjugates is the difference of their perfect squares. So it's going to be the square of the first guy, which is just x squared plus 9, minus the square of the second guy, which is 9. Right, and again, I typically do not multiply out in this case, the non-conjugate, the denominator. So let's see if we can't condense some steps down. So we know that 9 minus 9 is 0, so we're left with an x squared on top. And then we have an x squared and an x on the bottom. They will cancel out. So all told, we are left with, what are we left with here? We are left with x over the square roots of x squared plus 9 plus 3. And I think that's where we're left. Oops, I forgot the limit. See, that would have been bad. I would have got this problem wrong or points deducted. I haven't applied the limit, so I got to rewrite it. X over the square root of x squared plus 9 plus 3. Now I can go ahead and attempt to plug the limit in. And then if I plug it in, all that work gives me a 0 because I still have a 0 on top. So now I know some of you guys will whine, man, we did all that work for nothing. No, you didn't do that work for nothing. You've mathematically proved that the limit is 0. So algebra, you can use algebra with limits, provided that the function is, quote, nice enough. If the function is nice enough, just straight up plug and chug. If you ever get indeterminate form, 0 over 0, that usually means you have to do some sort of algebra manipulations or simplification before you can do so. One thing you can do is simplify, factor and cancel. Another thing you can do, straight up simplification. And another thing you can do, if you notice you have a radical with the binomial, almost always involves conjugates. So good luck, and practice finding these limits using algebra.